Okay, hi. I hope that you guys understand the previous theorems that I've shown you will shed more light on the interpretation of del phi, such as the direction of travel if you want the greatest directional derivative, and the other one is that it is perpendicular to the level surface. So, just giving a quick example, this is del phi. Now, we can't sketch this curve, but what we're going to do is that we let phi, sorry, this is phi, not del phi, this is phi over here, we let this equals to 0, okay, and then this is equal to 0, so when we arrange, we get roots x minus y squared, root x squared minus y squared equals to z. Now this we can curve, this level curve we can sketch because phi is equals to a constant. So if you were to sketch it, and if I were to do a quick one, okay, it would just simply give us a cone that goes like that. Okay, simply a cone over here. Okay, and the z-axis is here, over there. So this is interesting because the level curve is a parametric equation such as this, and we also have in a way the scalar field defined by phi like that to do manipulations. So obviously what we want to do is that we want to use the del operator, which is what I will do now, okay, and this would give us, let me just quickly find the solution, okay, minus x over zi plus minus y over zj, and then it is plus k over here. Okay, so using the del operator on phi, we get del phi, the gradient of phi, and it's a vector. Okay, so from the previous theorems, we know that this vector would be perpendicular to the surface as sketched out by the level curve. Okay, so for example, let's just say we have a point P0 over here. Okay, and P0, I must say again, it must rest inside the level curve. Okay, so P0 must exist, kind of drawn it like that inside this level curve over here. We put the values inside there, we get a vector. Yes, correct. The vector, it goes like that. Okay, and this vector is perpendicular to the surface, or the level curve as we have sketched it. So how do we test that? Well, recall your position vector R. Position vector R, x, y, z. Now what is position vector R? Position vector R is a vector that we go from the origin to the point, or whatever point we want to specify on the curve. In this case, let's make it point P0. So this is the position vector R here, and del phi is over here. Okay? Now, if R travels from the origin to P0 along that level curve, okay, and del phi is perpendicular to the level curve, if we dot the two of them together, we should get 0. Okay? So the position vector would be written as this. I hope it's easy enough to understand. The point is x, y, and z. We go from 0 to x, y, and z, so we need the components I, j, k. We dot the two of them together, okay? X, y, z. We dot them together, we get minus x squared over z, minus y squared over z, and plus z, okay? And then we will divide throughout by z, and this is plus z squared. Now z squared on the level curve is equals to this, so we take the z is equal to this, we take square this, it will be y squared minus x squared minus y squared, and we add with that, okay, and we get 0, just as expected. So that means, again, to prove that del phi is perpendicular to the position vector or the level curve. Lastly, let's find the equation of the plane over here. Okay, the equation of the plane that it is sharing a point of P0, that it is, how to say, tangential to the level curve. Now we know P0 is inside there, and P0 is x0, y0, z0. So a vector on the plane would be x minus x0, I, okay, plus y minus y0, j, plus z minus z0, k. And this is a vector on the plane, so a vector on the plane dot with the perpendicular vector del phi evaluated at P0 would give us 0. Okay? Put in, dot them together, write them down as a separate components, dot them together, you get the big equation, and that equation is the equation of the tangential plane. Quick example, I hope you like it.